Hi, this is John Mount of WinVector LLC, a data science consulting company. I'd like to share a couple articles we've written recently on dealing with uncertainty in optimization. Many optimization problems are killed because they don't handle uncertainty correctly. The three articles we have, which perform a sequence, are Modeling Uncertainty for Better Outcomes, which introduces uncertainty into optimization, Reducing Optimization Risk Through Portfolio Methods, which uses uncertainty to encode things like diversity of solution, which is a very important practical consideration often neglected. And then finally, Save Your Optimization Projects from the tuning trap, where essentially there's this over-optimization or overuse bias that is very much like machine learning overfit bias, but can be overcome. Now, in the individual argument articles, we have the classic optimization problem, optimize a linear function given to us from gosh knows where over a set of linear constraints, and then we find this vertex. However, we find this doesn't accurately model the real world situation where instead of one objective function, you have a family of objective function estimates, and you need to do well over that and pick an optimum that is not only optimal for your estimate of the objective function, but not bad for many of its near neighbors or analogs. The second article uses this risk methodology to reevaluate the minimal diet problem, a very famous diet problem. And what we're going to do is encode if we can take a nutrient such as niacin from two sources instead of one source, that's probably safer to do because any misestimate of the valuability of that source is now mitigated that we're now taking it from another source. So we use the re-encoding into risk and then the previous risk-aware solution to solve this. Finally, in the third article, we deal with this other issue of when you estimate an objective function and optimize against it, you tend to be overconfident in your solution. And that is you find a solution you think is worth $110, but then if you had access to the true objective function, say by going to market and trying your solution, you find out it's only worth about $35 and really embarrass yourself. And we show how a hold out early stopping technique, very analogous to what is done in machine learning, can not only find a slightly better solution, but also correctly report its value, which can be all that's required to maintain confidence in an optimization problem. Just don't say the wrong thing. Anyway, I hope you check out these three articles. They show some problems that are, I think, lurking in many projects and that once identified can actually be mitigated. Thank you for your time.